Hello everyone, I'm excited to welcome you to the online course Easy Geosteering. Here we simplify the complex geosteering topics, breaking them down into easy-to-understand concepts. We are currently in the second part of the course, BHA components, and in the previous video we covered rotary steerable system and the mud motor. And today we explore telemetry process and data density. Let's get started. During the drilling process, MLWD tools measure various formation properties, which then need to be transmitted to the surface. But how exactly does the transmission process work? Let's break it down using mud pulse telemetry as an example. First, MWD tool prepares data for transmission by encoding it into binary code, a sequence of zeros and ones. Meanwhile, the drilling mud in tubing space flows from the surface to the bottom of the well. When it reaches MWD tool, it passes through a special pulse modulator consisting of a rotor and a stator. In the open position, the drilling mud flows freely, while in the closed position, the pressure increases. By rotating at different frequencies, the rotor converts the binary code into pressure pulses. A low frequency represents 0, while a high frequency represents 1. Then pressure pulses travel in tubing space from the bottom to the surface. These pulses have a low amplitude, typically a few psi. At the surface, before drilling, MWD engineer installs signal pressure transducer, or SPT, special sensor on the standpipe. This sensor is highly precise and capable of detecting telemetry signal from the downhole tool. The signal is captured by SPT, and then the inverse process converts the pressure pulses back into binary code. This sequence of zeros and ones is sent to specialized MWD software, where it is demodulated, converted from binary code into standard LWD data. So we have covered telemetry process in a simplified way, and this process is inextricably linked to such an important concept for us as data density. The data density of a specific measurement, such as gamma ray or resistivity, is the number of valid readings of this measurement per 1 meter MD. For most geosteering tasks, a data density of 2-3 valid points is perfectly sufficient. If you have more, even better. Let's imagine we are drilling through a clean and consistent sandstone layer characterized by a gamma ray of 60 API. A high data density log will appear as a highly discrete curve with many gamma ray data points, while a low data density will look like a series of straight line segments. There is no actual gamma ray data in straight lines. These are merely interpolations between real surveys, which are located at the joint points. So, in the interval 1010-1020, we literally have 6 real gamma ray surveys at all. It means 0.6 point per 1 meter. Okay, we also mentioned that readings have to be valid. What does it mean? There are several factors which affect the quality of the telemetry signal. When MWD software receives a low-quality signal, the result of demodulation may be unexpected, or may not correspond to the lithology we are drilling through. Let's take a look at the interval from 1020 to 1030. At one point we get a gamma ray value of 100 API, followed by a low value of 20 API, which might be interpreted as a shale and a hard carbonate layer respectively. But the problem is there is only one data point at each level, and we cannot rely on it because in fact there are no other gamma ray data in the entire highlighted interval. We call these surveys spikes and consider them suspicious. What is an acceptable gap between real surveys? 10 centimeters, half a meter, maybe 1 meter or more? What do you think? Well, it entirely depends on the situation. As we mentioned, for most tasks, 2-3 points per meter are sufficient. However, having only 1 point per meter doesn't always mean bad data, because data density itself is not the ultimate goal, it's a merely control tool for us. For example, data density depends on the rate of penetration. The greater ROP, the lower the data density. Let's imagine we are drilling a horizontal section at high ROP of 80 meters per hour. If there is no risk of leaving the target layer, nobody will limit their OP just to increase the number of gamma ray surveys per meter. Okay, number 2. Data density also depends on the telemetry bitrate. Since it is the speed of data transmission, the greater the bitrate, the better the data density. Point number 3. During the programming of the telemetry tool, MWD engineer selects the frequency of each measurement. The more frequent the measurements, the higher the data density. Meanwhile, the data density of different channels may vary. For example, if gamma ray data is more important for a project, it might be measured every 10 seconds, while, for example, resistivity is measured every 20 or 30 seconds. And finally, the signal quality significantly affects data density. What does the signal quality depend on? The most common problem is pump noise. During mud circulation, the plungers move back and forth at a certain frequency, and this might interfere with SPT sensor's ability to receive a useful signal from MWD tool. Second point, signal attenuation. Due to friction losses, the deeper the well, the weaker the signal. Additionally, if the drilling mud is too viscous or contains foam, it will also weaken the signal. Point number 3. Any type of mechanical drilling noise, such as shocks, vibrations, and stick slips, falls within the spectrum and may affect signal quality. And point number 4, electrical noise. This situation can occur only on the surface, for example when the cable from SPT sensor is lying near an unshielded power cable on the rig. In this case, electrical interference will affect the digital signal on its way from SPT to MWD station. So, we have covered the data density and the basic principles of mud-pulse telemetry. Now, to complete the picture, let's take a look at the main tool types that operate with a continuous wave. All of these tools use a rotor-stator pair and follow the same working principle, but they differ in design and are tailored for different tasks and budgets. The first type is slow and retrievable telemetry. It's a slim and long tool that can be placed in different size collars for different hole sections. On the top it has a fishing head, which allows us to pull out the tool in case of a stuck pipe incident. Lower we can see the rotor and stator, which generate the mud pulse signal to the surface. This tool is powered by a lithium battery, which limits its operating hours and telemetry speed. The maximum bitrate is about 1 bit per second. For example, a gamma ray data point takes around 8 bits, which means we need 8 seconds to transmit just one measurement to the surface. Along with gamma ray, this tool also measures inclination and azimuth, but because of the low bitrate, it can only be used with a mud motor, as the rotor steerable system requires higher bitrate and more steerable data for transmission. For the same reason, this tool is typically used alone, without any other LWD tools in the BHA. The second type is fast telemetry mounted in a collar of a constant size. It also has a rotor and stator, but this tool is powered by a turbine, which generates energy from the drilling mud flow. The bitrate is much higher, up to 12 bits per second, so a gamma ray data point takes about 1 second or even less to transmit. This tool provides the same basic measurements, gamma ray and DNI, but due to high bitrate it can work with RSS, and in addition it's able to transmit the full data set from various LWD tools, such as resistivity, neutron density, and others. And type number 3 is fast telemetry with resistivity sensors on board. It's like a hybrid between MWD and LWD tools. It includes several electromagnetic coils to measure formation resistivity, which makes it look different from the other downhole tools. Its performance is similar to Type 2. It can work with RSS and LWD tools, and it also combines gamma ray, DNI, and resistivity in a single collar, reducing the distance to the bit for these measurements. Alright, we have covered the main points of MWD tool. Hope you like this video. Remember, you can take your geosteering skills to the next level with private lessons. In StarSteer we use drilling simulators to give you an experience of a real geosteering engineer. Stay tuned and give this video a thumbs up. In the next lesson we will explore LWD logging. See you then. Bye bye.